There is evidence that Mars in the past had an ocean in its giant North Polar Basin that takes up 1/3 of its surface. In that basin, there are large-scale flow patterns along with direct evidence of water ice beneath the surface, which is revealed by fresh impact craters. This is a rendition of what Mars looked like in the distant past. Although it isn't exactly known what Mars looked like back then, it does a good job of visualizing where the ocean was. However, besides the ocean, it also accurately shows craters filled with water, and that is because there is good evidence that these lakes existed, and they did so in abundance. A 2008 study identified 210 open basin lakes on Mars. This is a map of where those lakes are located. There were two conditions used to determine whether or not a crater was filled with water. One is that the crater must be a basin such that if lots of rain were to fall, or if groundwater started pouring, the water would pond. And the second condition for determining whether or not a crater was a lake is if there is an outlet, basically this channel feature that is created as a result of water flooding the basin enough to cause a breach. The outlets are typically at a higher elevation compared to the floor of the basin. There is also evidence that many of those channels were connecting different crater lakes together, forming huge lake chains through valleys that stretch for many hundreds of kilometers all over the Martian landscape. Out of 210 identified lakes, 130 lakes were likely a part of a lake system. The largest lake system stretched for 4,500 kilometers. This image shows 4 huge lake systems. The blue lines represent the lake surface area, and the white lines the insanely long valleys that connected different lakes. So the evidence for lakes on Mars is pretty abundant, but probably the most impressive lake on Mars in the past was Eridania, which is also likely the largest lake that Mars had. So large that calling it a sea is also appropriate. Somewhat far from the ancient Martian Ocean, in the southern highlands of Mars, there is an area containing a few interconnected basins that were likely filled with water. In this way, it clearly differs from most of Mars's ancient lakes, which were only a singular circular basin that resulted from a single impact. These few interconnected basins were at an early point in Mars's history also craters, but over time they had their sharp edges eroded. So a huge open area for a water to get contained and form, and water did get trapped, both as a result of rainfall and also as a result of groundwater welling up. In fact, it appears that there isn't enough watershed, that is, regions that channel rainfall from the surroundings to the basins to conclude that Eridania was mostly filled by rainfall. Rather, it had to be the case that groundwater welled up and helped fill in these huge basins. Water was also sufficiently contained in the Eridania lake such that it started spilling over. That's how the outlet channel called Ma'adim formed. We can see how its outline clearly starts at higher elevations, quite a bit above 0 meters, right next to the Eridania lake. And then the channel is very gradually lowered to the floor of the Gusev crater, which is about 1,500 meters below the 0 meter point. Based on the elevation of where the Ma'adim Valley starts, it was concluded that the water level of the Eridania lake was at an elevation somewhere between 700 meters and 1,100 meters. This is an unusually elevated water level when compared to other lakes of Mars. However, large parts of the lake were also below the 0 meter point of Mars, so the deepest points in the lake are about 500 meters below the 0 meter point. So yes, this means that this lake was at certain parts between 1 and 1.5 kilometers deep, so about as deep as the deepest lake on Earth. So Eridania still had immense pressure at the bottom, even with Mars's significantly weaker gravity compared to Earth. In this image, we can see how, depending on where the water level was at, the difference in surface area of the lake also varied a lot. So the white outline shows the surface area of the lake if the water level was at an elevation of 700 meters, and the black outline shows what the surface area of the lake was if the water level was at an elevation of 1,100 meters. Both water levels also connect right to where the Ma'adim Valley starts and descends, so both are plausible. The overall approximate estimate of the surface area of this lake, or rather sea, is 1.1 million kilometers square, meaning Eridania was larger than any currently present lake on Earth, and it's not even close. The Caspian Sea, which is actually a saltwater lake, has a surface area of 371,000 kilometers square. The Great Lakes in North America, which are the largest freshwater lakes, all of them combined have a surface area of 244,000 kilometers square. So yes, Eridania had a surface area probably about double that of the Caspian Sea and the Great Lakes combined. To get some perspective on just how large 1.1 million kilometers square is, this is mainland United States, and the circle shown here represents a surface area of 1.1 million kilometers square. So yeah, the Eridania lake, or rather sea, was huge. Based on the surface area and the depth of the water that Eridania plausibly occupied, a conservative estimate of the water volume that was present in the lake was calculated. This neat figure shows us the comparison of the water volume between different significant bodies of water. So, as clearly visible, even the conservative estimate of the water volume of the Eridania lake shows us that it had about as much water as all of the Martian lakes combined, and the water volume is also far greater than that in the Caspian Sea, Baikal, and the Great Lakes. Now, the water volume still does pale in comparison to the Mediterranean Sea, but that makes sense given that the Mediterranean Sea has at least double the depth of Eridania and also probably double the surface area of Eridania. Still, it's not like Eridania is so small compared to the Mediterranean Sea that it can't be seen, and that alone is impressive for a highland lake on Mars. Today, probably the key feature of Eridania are its deepest parts, with ground that contains chaotic terrain. This feature on Mars is appropriately named chaos. The floor of these regions eroded into countless hills, which are commonly flat-topped. After that, volcanic materials blanketed these regions. This image shows the structure of the basins. We can see that the hills are actually an extension of a deeper basin deposit, and then on top of most of that deposit, there are volcanic materials that later blanketed the deposits. These deposits are at least a 400-meter thick layer of clay, and they are at the deepest part of Eridania, so they formed deep underwater. So the most likely explanation for how these extremely thick clay deposits got to be in the floor of the basins is through explosive vents. With that, it is very likely that this lake had very active hydrothermal vents. Using the data gathered by the Mars Reconnaissance Orbiter, specifically the data from its spectrometer instrument, the basin deposits were analyzed, and it was detected that they are iron-rich clay. Spectrally, these basin deposits are similar to iron-rich seafloor deposits sampled on Earth. The reason this evidence of hydrothermal vents is so interesting is because, on Earth, hydrothermal vents are brimming with life even at depths where there is no sunlight. The warm and nutrient-rich environment near the hydrothermal vents is great for life. This image gives a nice overview of the water depth over the main part of Eridania, right where the basins are. As we can see, most of the deposits are located in the deepest parts of the lake, where the pressure was the greatest. If the water level was at an elevation of 700 meters, then that means that the deposits formed between 500 and 1,200 meters of water depth. And considering the weaker surface gravity of Mars compared to Earth, these basin deposits formed at a pressure between 20 and 50 bars, so between 20 and 50 times greater pressure than the surface pressure on Earth at 0 meters. This great pressure at the bottom of Eridania also affected the type of volcanism that was present. It likely had explosive periods, along with periods of where material poured gently out of the hydrothermal vents. Corales Chaos is the central basin of Eridania. On the ground of this basin, there is a 17-kilometer wide crater. In the central peak, in the rim, carbonates, a type of salt, was detected. Potentially that material formed as a result of impact-generated hydrothermal activity, or that material was possibly uplifted during an impact from 1 to 2 kilometers below the floor of the basin. On top of this map showing the water depth level, and with that, differences in water pressure, it also neatly separates where different types of materials are present. The really deep parts, marked in blue, are also where the clay deposits were found, while the really shallow parts, marked in red, are where mostly chloride was found. The study that found evidence of ancient hydrothermal vents in Eridania has this to say about chloride deposits. The average elevation of chlorides is 660 meters, which is similar to the low water level of Eridania Sea, 700 meters, suggesting they may have formed through evaporation in shallow seawater near the basin margin. In this image, we can see differences in elevation between clay and chloride deposits. The thick clay is mostly at very deep parts, and also at some high elevation parts, but the thin chloride deposits are exclusively at higher elevations. These two enhanced color images show how the chloride deposits look like from a satellite. Overall, the topography of the basins that are present in Eridania are relatively unique for Mars. Most basins have flat floors, while the basins of Eridania are concave. This unusual shape was achieved exactly because a huge layer of water protected the basins. The shape and crater counts of Eridania point towards these basins being protected under a layer of water during the late Noachian, which had very intense impact activity, along with surfaces constantly being reburied. Here we can see the different periods of Mars. So the late Noachian period was around 3.8 billion years ago. After that, it appears that Eridania dried out. But before 3.8 billion years ago, it appears that Eridania existed for a long time, likely many tens of millions of years, and quite possibly 100 million years and more. Also, it was concluded in the study which showed ancient hydrothermal vents in Eridania that the deposits in the Eridania basins did not have airfall origin, as the deposits are not layered, are extremely thick, and only present on very low elevations. The airfall deposits on Mars typically have the exact opposite of those three traits, as in they are layered, are thinner, and are present more evenly at a variety of elevations in a region. This is a geologic model of the Eridania Basin, so we can see the hydrothermal vents, the clay deposits that those vents helped create, along with all of the chemicals which were detected in that clay, the thin chloride deposits at higher elevations, the groundwater which, as already said, likely contributed massively to the filling of the basin with water, the different plausible water levels, and finally, there was maybe an ice cover at times. This, however, is very uncertain, but far from impossible. The Eridania Lake was not exactly at the equator. It was at a latitude of about 35 degrees south, so the seasons that Mars has alone could have potentially led to a winter ice cover. Or maybe there were long periods of where ice cover was present for many years in a row due to a global change in climate. Whatever the case was, because of hydrothermal vents, potential life forms that existed there could have been supplied with hot water along with nutrients at the bottom of Eridania, even underneath a thick layer of ice. The closest we got to exploring Eridania as of now is NASA's Spirit rover, which reached Mars in 2004 and landed in the crater called Gusev. It was exploring the center of this crater. Now that crater is the exact same one which was flooded through the Ma'adim Valley by the waters of the Eridania Lake. However, this is still a very indirect exploration of the past waters of Eridania. This image showed us that Eridania had a huge volume of water. It appears that the water volume of all other Martian lakes combined was similar to Eridania. This volume was calculated through the size of the basins along with the elevation that their outlet channel started at, which gives us the water level. However, there is one lake, or rather sea, that potentially contained a lot more water. So much water that it is similar to the Mediterranean Sea, and that water volume was likely located in Argyre. Argyre is a basin quite a bit further south compared to the Eridania basins, so it is closer to the South Pole. And there is evidence that in the very distant past, there was an ice sheet in that place that was struck by an impact. That impact then melted the water in that ice sheet and created a gigantic sea in Argyre. Then, due to the frigid temperatures, that giant sea started freezing again. However, because that impact generated so much heat, and with that likely volcanism, there were still likely hydrothermal vents that heated the deep parts of the lake and potentially kept it liquid even underneath a thick layer of water ice for many millions of years. That environment of Argyre is also promising for detecting the evidence of past life on Mars. So there is evidence of large bodies of water on Mars throughout a variety of latitudes and elevations. It is somewhat impressive that Mars in the past had a thick enough atmosphere such that even at comparatively high elevation of Eridania, the atmospheric pressure was still great enough to allow for the existence of a giant lake. Fast forward to today, and the atmosphere of Mars has only about 0.6% the pressure of Earth. Certainly not enough for even ponds of water, and even the deepest parts of Mars, where the pressure is much greater, so in the Hellas Basin, even those extremely deep parts aren't capable of having even small lakes, although some extremely tiny parts with salt water could exist in a liquid state at those places. As of now, there are no publicly known plans to explore the Eridania basins or the Argyre basin with rovers. And with that, it appears that in this decade, we still won't get a single rover or even a lander that successfully lands and delivers images from the surface of anywhere deep in the southern highlands of Mars. Meanwhile, this map shows that we already had 10 successful landers or rovers that were either directly in the North Polar Basin or close to it. One future rover mission on Mars is the European Space Agency's Rosalind Franklin rover. However, this one is solar-powered, not nuclear-powered like NASA's Curiosity and Perseverance rover. Because of that, Rosalind Franklin is more limited in sites that it can land on and last for a long time. So a place very close to the equator was chosen because those provide sunlight a lot more consistently compared to high-latitude places. The landing location chosen is also in the North Polar Basin, more specifically in Oxia, which is in the vicinity of the Mars Pathfinder lander and rover. Hopefully, however, in the future we are going to get a nuclear-powered rover that lands either in Eridania or Argyre. And no, the hilly nature of the southern highlands isn't what is preventing the exploration, as there are vast flat areas that are safe to land on, and with current technology, landing sites can be pretty specific.